Hello friends, welcome back to my YouTube channel. This is 10th part of my discussion on mass transfer coefficients, and I will continue my discussion on prediction of mass transfer coefficients in turbulent flow. And there are different theories of mass transfer for predicting mass transfer coefficients in turbulent flow, and I have started my discussion on theories of mass transfer since the last lecture, part number 9. So in part number 9, I discussed film theory, and today I will be discussing penetration theory that is used for predicting mass transfer coefficients in turbulent flow. So let us begin the discussion. What is the background? Let us first understand. In practical chemical engineering operations, turbulent conditions are always preferred. What is the reason for that? Under turbulent conditions, we get high heat and mass transfer rates. That's why turbulent conditions are always preferred. But the problem with turbulent conditions is they cannot be represented mathematically. No equations are available. It is difficult to get mathematical equations that can describe turbulent conditions. So therefore, theoretically, it is not possible to predict mass transfer coefficients under turbulent conditions because we don't have those equations that can be used to theoretically predict the mass transfer coefficients under turbulent conditions. So what can be done? One way is you can have experimental prediction. You can carry out experiments and use the experimental data to predict the mass transfer coefficients under turbulent conditions. But the experimental prediction, it has a limited scope because it is possible only in limited situations and circumstances, and it is possible for a limited range of fluid properties. So experimental prediction is not possible in all cases. Therefore, whenever there is no experimental data, whenever it is not possible to predict the mass transfer coefficients experimentally, we need a mechanism for predicting mass transfer coefficients. There is a need for predicting mass transfer coefficients in the absence of experimental data, and this is done by the mass transfer theories. So there are mass transfer theories available in the literature that are used to predict mass transfer coefficients in turbulent flow. Film theory is the simplest and the oldest theory in this case. I have already discussed it in part number 9. I am giving link to the entire playlist of my video lectures on mass transfer coefficients in the description section. If you have not yet seen those videos, you please watch those videos. So for predicting, in the absence of experimental data, for predicting mass transfer coefficients, we have mass transfer theories. Let us move ahead. So what are these mass transfer theories? You have many mass transfer theories that are available for predicting mass transfer coefficients in turbulent flow. Many mass transfer theories are available in the literature, but these mass transfer theories, these are mere speculations. These are just imaginations. These are mere speculations, and they are constantly renewed as new observations are made, new experimental data is collected, as new research is done. These mass transfer theories, they are constantly renewed. Now let me list the important mass transfer theories which I will be discussing. The first one is film theory. I have already discussed it. Then you have the penetration theory, which I will be discussing in this video lecture, and then you have surface renewal theories. Then you have combination film surface renewal theory and surface stretch theory. So these are the important mass transfer theories which I will be discussing in my video lectures, and today I will be discussing the penetration theory. I have already discussed the film theory in part number 9. So let us continue. Now let us talk about the penetration theory. Penetration theory, it was proposed by Higby in 1935, and it is applicable to mass transfer between two insoluble phases that are in contact with each other, and one phase is under turbulent conditions. So when you talk about two insoluble phases, then there are two possibilities. It could be gas and liquid, in which the liquid is under turbulent conditions, or it could be two insoluble liquids in which one of the liquid is under turbulent conditions. So if mass transfer is taking place between two such phases, then you can predict the mass transfer coefficients by using penetration theory. The theory, what does the theory predicts? The theory predicts the following thing. According to theory, EDs are formed in the turbulent liquid. So the liquid that is under turbulent conditions, EDs will be formed. And these EDs, they will come to the interface and they are exposed to mass transfer when they come to the interface between the two phases. So for example, you have the two phases. Let us say that liquid and gas, and as we said, liquid is under turbulent conditions. So EDs will be forming in the turbulent liquid, and these EDs, they will be constantly coming to the surface, interface between gas and liquid, and when they come at the interface, they will be exposed to mass transfer. When they come to the interface, let us say that a component in the gas, E may be, or he may get absorbed into this ED. So each ED, all these EDs, they will be coming to the surface and they will be exposed to this mass transfer. So what does this theory say? Let me tell you. Firstly, I hope you have understood the scenario. I will explain it in details later. Let me first erase it so that I complete this discussion. Just a minute. So you have the EDs in the turbulent liquid, which are constantly coming to the interface between the two phases and where they are exposed to mass transfer. Now the theory predicts that the exposure time, the time for which EDs come to the interface and they are exposed to mass transfer, this exposure time is same for all EDs, all the EDs. This is the prediction of penetration theory. The exposure time is same for all the EDs, and it is very, very short. Two things. One is the exposure time is same for all the EDs, and the second thing is it is very, very short. And due to this very short exposure time, steady state conditions will never be established. So as the film theory predicted that mass transfer occurs under steady state conditions, here according to penetration theory, the time of exposure is very, very short, and under that circumstances, steady state conditions will never be established. So therefore the penetration theory predicts that the mass transfer occurs under unsteady state conditions. So according to penetration theory, in this contact between two insoluble fluid phases, mass transfer occurs under unsteady state conditions. Why? Because the time for which mass transfer occurs, it is very, very short. So this is the prediction of this theory. In general, in brief, you can write the prediction in this way. ED is formed in the turbulent liquid. They come to the interface. They are exposed to mass transfer. The time of exposure is same for all the EDs. The time of exposure is very, very short. Therefore, steady state conditions will never prevail. And that's why this is a case of unsteady state mass transfer. I hope you have understood the idea. If you have any doubts, you please mention them in the comment section. Let us move ahead. The mass transfer problem, let us understand. In order to understand it in more detail, I will be discussing two examples. So let us consider a mass transfer problem. What is the mass transfer problem? Absorption of gas A into liquid B. So the task is to absorb liquid A, gas A into liquid B. And what is done? The gas is made to rise as a bubble through a column of liquid in in a glass tube. So we are considering a scenario where we are making the gas to rise as a bubble through a column of liquid in a glass tube. I will show the schematic diagram. So you have the glass tube, liquid is filled in it, and there is the gas bubble, gas E, and the gas bubble rise through the liquid column. So gas bubble will be rising through the liquid column in this way. So as the gas bubble rises, what happens? It leaves behind the displaced liquid. So you can easily understand, as the gas bubble is rising, it will be leaving behind. So as it rises, it leaves behind a liquid film between the tube wall and the gas bubble. So you can easily understand. So as the gas bubble is rising, it will be displacing the liquid, and then the liquid, it will be forming liquid film between the tube wall and the gas bubble. So as the gas bubble rises, it leaves behind the displaced liquid, and this displaced liquid, it forms a thin film between the gas bubble and the tube wall. So let me show you the scenario. So you have the glass tube and gas bubble is rising through it. I have shown that. So when it rises, as the gas bubble rises, so it is displacing the liquid, and then liquid will be forming a film between the gas bubble and the tube wall. So this is what happens if you have this situation. The gas bubble rising through the column, and while it rises, it displaces the liquid, and the displaced liquid then forms a thin film between the gas bubble and the tube wall. So it is assumed that each element of the liquid in the film is exposed to the gas. So whatever film it is formed, in this case, each liquid particle in the film, it is exposed to mass transfer. That means when you have the film, each liquid particle in the film is in contact with the gas bubble. In other words, each liquid particle is exposed to the gas in this gas bubble, and the theory predicts that this exposure time is same for all the liquid particles. I mean, the exposure time is very short. I will talk about it. I hope you have understood the situation, the scenario. Let us move on. So now, in the same case, let us consider a liquid particle on the top of the gas bubble. So you have the column of liquid, and now we are considering an instant where you have the gas bubble and a liquid particle is at the top of this gas bubble. So we are starting at this instant. So what happens as the gas bubble rises through the water column? So as the gas bubble moves up or rise through the water column, what happens? This liquid droplet, this liquid particle slides down. The liquid particle slides down. You can imagine. So as the gas bubble rises through the column, this liquid particle will be sliding down the gas bubble. And now the gas bubble and the liquid particle, if this is the case, the gas bubble and liquid particle, they will be separated once the gas bubble rises through a distance equal to its diameter. So as the gas bubble rises through a distance which is equal to its diameter, this liquid particle will complete its journey. One journey of starting from the top and sliding down the gas bubble, and then coming down and leaving the gas bubble. So the gas bubble and liquid particle will be separated once the gas bubble rises through a distance equal to its diameter. That means in this case, the time of contact is the time taken by the gas bubble to rise through a distance equal to its diameter. and the theory says that this time is very short. So we can see now the gas bubble has moved up and the liquid particle had slided down. And again, as the gas bubble moves up, the liquid particle has come down, and now it will leave the gas bubble. So the time of contact in this case is very short. We are going to denote time by theta. So the time is equal to the time taken by the gas bubble to rise to a distance equal to its diameter, theta, very small. So for due to this case, that is the time of contact is very short, the concentration profile, that is characteristics of steady state, it will never establish. The time of contact is very short for the concentration profile characteristics of steady state to establish, and therefore this is a case of unsteady state mass transfer. This is a case of unsteady state mass transfer. So the time of contact for mass transfer between the two phases, it is very short, and it will not be enough for steady state to get established, and therefore it is a case of unsteady state mass transfer. Now next we will discuss one extension to this mass transfer problem. So let us go ahead. Now we will discuss an extension to this mass transfer problem. So again, the problem is absorption of gas A into liquid B. Now in this case, the liquid is in a pool that is under turbulent conditions, and it is in contact with the gas E. So you have the liquid pool. Now I will show the liquid pool. The liquid pool, liquid B, is under turbulent conditions. It is under turbulent conditions, and it is in contact with the gas E. Let me just complete the schematic diagram. So you have the liquid pool. So this is the liquid pool which is under turbulent conditions, and now it is in contact with gas E. So you have liquid B that is under turbulent conditions, and it is in contact with gas E. So let us consider an ED. This rectangular block that I have shown over here is an ED, which is initially present in the turbulent depth. And what will be the journey of this ED? Let me tell you. So it will rise up, it will come to the surface, and once it comes to the surface, it will be exposed to gas E, and then gas E will be dissolving into the liquid, and there will be mass transfer. It will remain on the surface for a very short time, and then it will again go to the turbulent depth. So an ED which is initially in the turbulent depth, it rises to the surface. At the surface, it is exposed to mass transfer. The exposure time is very short, and after this short exposure, it again returns back to the turbulent depth. So I have shown the journey. So initially the ED is at the depth, turbulent depth. It rises to the surface. It remains at the surface, and then again it comes back to the turbulent depth. So if you talk about an individual ED, within the individual ED, concentration is uniform. Within individual ED, the conditions are stagnant, and concentration is equal to the initial concentration of A in the liquid, Ca0. In this case, Ca0 represents initial concentration of A in the liquid. So within individual EDs, the concentration is Ca0. Within individual EDs, the conditions are stagnant. So this is true for every ED. I have just shown one ED. The thickness of the ED, I am going to denote it by ZB. Thickness of the ED is ZB. So within individual EDs, the concentration is equal to the initial concentration in the liquid, which I will be denoting by Ca0. and then on the surface it will be exposed to the mass transfer. So at the surface in the liquid, the concentration of A is CAI. What is CAI? CAI is concentration of A in the liquid at the surface, at the interface between gas and liquid. So you have CAI at the surface. So the driving force in this case is CA naught and CA naught, CAI minus CA naught. Due to this driving force, mass transfer is taking place, and the time for which the ED remains at the surface, let that be theta. And we have understood, as per this theory, this theta is same for all the EDs, and plus it is very, very short. That's why steady state conditions will never prevail. It will always be unsteady state mass transfer. So I hope you have understood the extension of the previous mass transfer problem. What you have to remember, every ED in the turbulent liquid, it will be coming to the surface, it will be getting exposed to mass transfer, but only for short time, and this time is same for all the EDs. That is the prediction of penetration theory. So I hope you have understood this. Let us move ahead. So EDs are formed in the liquid B. Stagnant conditions prevail with an individual ED. I have told you. EDs are initially in the turbulent depth and they constantly come to the surface, and at the surface they are exposed to gas A where mass transfer occurs. This is what happens. Now each ED, if you have to talk about each ED, it has stagnant conditions within it, is initially in the turbulent depth, comes to the surface where it is exposed to gas E, but only for short time. The time of exposure, according to this theory, it is same for all the EDs, and when you have short exposure time, this is a case of unsteady state mass transfer. Why unsteady state mass transfer? Because there is no enough time for steady state conditions to prevail. So the theory predicts that since the time of contact is very, very short, there will always be unsteady state mass transfer. Steady state conditions will never get established. So I hope you have understood what is the idea behind the penetration theory. Let us move ahead. So we have the scenario represented in this schematic diagram. So as we understood, this is a case of unsteady state mass transfer, and this unsteady state mass transfer, it is described by the following equation: dava Ca by dava theta, that is equal to dAb dava square Ca by dava Z square, and I am going to call this as equation number 1 in my discussion. So equation 1 describes the unsteady state mass transfer that occurs in this case. So in this case, Z is measured along the thickness of the ED. So we are measuring the Z along the thickness of the ED. ZB is the thickness of the ED. Now in this case, A is never able to cover the entire thickness of the ED. Again, this is the prediction. According to this theory, when A goes into, or when A enters an ED, it will never be able to cover the entire thickness of this ED. That is, it will never be able to cover the distance ZB. So for A, ZB is as if it is an infinite distance. So A is never able to cover the entire thickness of the ED. And the exposure time theta, it is too short. Why? We are understanding why it is not able to cover the entire distance. We are saying that A is never able to cover the entire thickness of the ED. And what are the reasons? There are two reasons for this. One is the exposure time theta is too short. And the second one is diffusion of A through the ED, it is very slow. due to very short exposure time and due to very slow diffusion of E, he is never able to cover the entire thickness of ED, that is ZB. So as I said, thus for A, ZB is essentially infinite. So for A, ZB is essentially infinite. It will never be able to cover this distance. What is the reason for that? One is the exposure time is too short, and the other reason is within the ED, the diffusion is very slow because it is molecular diffusion. Why molecular diffusion? Because stagnant conditions prevail within individual EDs. Let us move ahead. The differential equation, we need to solve it in order to get the equation for mass transfer rate. So the differential equation is solved subjected to the following boundary conditions. Which are the boundary conditions? At the start, that is at theta is equal to 0, Ca is Ca naught everywhere for all z's. So at theta is equal to 0, Ca is Ca naught for all z's. Then at z is equal to 0, when you are at the surface, Ca is equal to Cai, and this is true for every theta. So at z is equal to 0, Ca is Cai for all thetas, and at z is equal to infinity, that is within the turbulent depth, at z is equal to infinity, Ca is again Ca naught, and this is true for all thetas. So we will be solving equation number 1 subjected to this boundary conditions. Let us move ahead. So we have equation 1, dabba Ca by dabba theta is equal to dab dabba square Ca by dabba z square. So the boundary conditions are at theta is equal to 0, Ca is Ca naught for all z's. Then at z is equal to 0, Ca is Cai for all thetas greater than 0. At z is equal to infinity, Ca is Ca naught for all thetas greater than 0. Now we are going to, in order to solve equation number 1, what we will do, we will write equation 1 in terms of a deviation variable, and I will be denoting that deviation variable by C dash. And how is C dash defined? C dash is defined in this way. C dash is deviation of Ca from Ca naught. So C dash is Ca minus Ca naught. So if I differentiate it with respect to theta, dabba C dash by dabba theta, so that is dabba by dabba theta of Ca minus Ca naught, and since Ca naught is not changing with respect to theta, it is considered to be constant. So therefore dabba C dash by dabba theta will be dabba Ca by dabba theta. Then let us differentiate with respect to z, dabba C dash by dabba z, that is dabba by dabba z of Ca minus Ca naught, because C dash is Ca minus Ca naught. So Ca naught is again constant with respect to z as well, so therefore it will be dabba C dash by dabba z is equal to dabba Ca by dabba z. If I differentiate it once again, it will be dabba square C dash by dabba z square, that is equal to dabba square Ca by dabba z square. That means equation number 1 now it can be written in terms of C dash. So it will be dabba C dash by dabba theta, that is equal to dab dabba square C dash by dabba z square, and I am going to call this as equation number 2. What we have done, we have replaced dabba Ca by dabba theta by dabba C dash by dabba theta, and dabba square Ca by dabba z square by dabba square C dash by dabba z square. So let us continue with this. So we have this equations, and we wrote equation number 1 in terms of C dash, the deviation variable, and C dash is defined in this way. C dash is equal to Ca minus Ca naught. Now we also got equation number 2, which is in terms of C dash. It is dabba C dash by dabba theta is equal to dab dabba square C dash by dabba z square. Now the boundary conditions which are in terms of Ca, we will convert them in terms of C dash. So we will start with the first boundary condition. So first boundary condition is at theta is equal to 0, Ca is Ca naught. And what will be the value of C dash in this case? C dash, which is defined as Ca minus Ca naught. But at theta is equal to 0, Ca is Ca naught. So C dash will be equal to Ca naught minus Ca naught, that is 0. And then at Z is equal to 0, Ca is Cai. And C dash, which is defined as Ca minus Ca naught, but at Z is equal to 0, Ca is Cai. So therefore C dash will be equal to Cai minus Ca naught. And the third boundary condition is at Z is equal to 0, Ca is Ca naught for all thetas. That means C dash, which is defined as Ca minus Ca naught, and since Ca is Ca naught, it will be C dash is equal to Ca naught minus Ca naught, which is again 0. So therefore now we have new boundary conditions in terms of C dash. First one is at theta is equal to 0, C dash is equal to 0 for all Z's. Then at Z is equal to 0, C dash is Cai minus Ca naught for all theta that is greater than 0. And at Z is equal to infinity, C dash is equal to 0 for theta greater than 0. So in this way, we expressed equation number 1, which was in terms of Ca. We expressed it in terms of C dash, and then accordingly we have changed the boundary conditions. So now in terms of C dash we have new boundary conditions, and we will be using this for solving the differential equation. Let us move ahead. If you have any doubts, you please mention that in the comment section. So we have equation 2, dabba C dash by dabba theta is equal to dab dabba square C dash by dabba Z square. New boundary conditions we got: at theta is equal to 0, C dash is 0 for all Z's. At Z is equal to 0, C dash is Cai minus Ca naught for theta greater than 0. At Z is equal to infinity, C dash is equal to 0 for theta greater than 0. Now equation number 2, what can you say about equation number 2? It is a differential equation. It is of first order with respect to theta time, but it is of second order with respect to Z. And the most convenient way of solving such a differential equation is to use the method of Laplace transform. So we are going to use the method of Laplace transform for solving equation number 2, the differential equation. So for that, what we will do, we will take Laplace transform on both the sides of equation 2. So Laplace transform of dabba C dash by dabba theta is equal to, what is the Laplace transform of this differential? It is S C dash of S minus C dash of 0. But C dash of 0, that means at theta is equal to 0. The value of C dash at theta is equal to 0. And we know that value of C dash, which is, if you remember, C dash was defined as Ca minus, let me use a different ink. So C dash, just let me tell you. So we had defined C dash as Ca minus Ca naught, the deviation variable. And C dash of 0 is nothing but the value of C dash at theta is equal to 0. At theta is equal to 0, Ca is Ca naught. So it will be Ca naught minus Ca naught, that is 0. So that's why Laplace transform of dabba C dash by dabba theta is S into C dash of S. Then Laplace transform of the other term, this term, dab dabba square C dash by dabba Z square. So dab is constant, so you can take out of the Laplace transform. So it will be dab into Laplace transform of dabba square C dash by dabba Z square. So that is Laplace transform of dab into dabba square C dash by dabba Z square is dab into dabba square C dash of S by dabba z square. Why this is the case? Because Laplace transform is independent of z. Laplace transform is independent of z. So it is dab dabba square c dash of s by dabba z square. So we can write in this way. And what is the reason for that? The reason is Laplace transform does not depend on z. So I hope you have understood it. If you have any doubts, you please mention them in the comment section. Let us move ahead. So we have equation 2, dabba c dash by dabba theta is equal to dab into dabba square c dash by dabba z square, and we had taken Laplace transform on both the sides of equation 2. So Laplace transform of dabba c dash by dabba theta is equal to Laplace transform of dab into dabba square c dash by dabba z square. We got equations for this. Laplace transform of dabba c dash by dabba theta is s into c dash of s, and Laplace transform of dab dabba square c dash by dabba z square is dab into dabba square c dash of s by dabba z square. So if we use it in equation 2 will be s into c dash of s, yes, that is equal to s into c dash of s is equal to dab into dabba square c dash of s by dabba z square. So that is, if I rearrange it, so it will be s upon dab. I am bringing dab on this side, so this is s upon dab into c dash of s, that is equal to dabba square c dash of s by dabba z square. That is dabba square c dash of s by dabba z square, and if I take this term to this side, it will be minus s upon dab c dash of s, that is equal to 0, and I am going to call this as equation number 3. Now what can we say about equation number 3? Equation number 3 is a linear second order differential equation in c dash of s. So it is a linear second order differential equation in c dash of s, and with the solution method we are going to solve it, and the solution method that we will be using, it depends on the nature of the roots of its characteristics equation. So our next task would be to write the characteristics equation for the differential equation and check its roots, and based on the nature of the roots that we get, we will use a method, we will use an appropriate method for solving this linear second order differential equation. Let us move ahead. So we have equation number 3, dabba square c dash of s by dabba z square minus s upon dab into c dash of s is equal to 0, and the solution the task is to solve this, and the solution method it will depend on the nature of the roots of its characteristic equation. So first task is we are going to check the nature of the roots of the characteristic equation. So let us first get the characteristic equation. So for that I will write the differential equation in a different form. So equation number 3, I am going to write it like this: dabba square c dash of s by dabba z square, plus there is no first order differential term, so I am bringing that in the equation by multiplying it with 0. So 0 into that term is 0. So it is dabba square c dash of s by dabba z square plus 0 into dabba c dash of s by dabba z minus s upon dab into c dash of s is equal to 0. So for a second order differential equation of this form, the characteristic equation will be of this form. It will be, let us say, mx square plus nx plus r, and in this characteristic equation, capital M is the coefficient of the second order differential term, m is equal to 1. N is the coefficient of the first order differential term, that is 0, and r is the third term, the coefficient of the third term, that is minus s upon dab. So first we will check what is the nature of this characteristic, nature of the roots of this characteristic equation, and based on that nature we are going to decide the method that we can use for solving this second order linear differential equation. So let us understand this. So for that we need to evaluate the discriminant. of this characteristic equation. And how are we going to get that discriminant? Discriminant delta is n square minus 4 m r, and these are the values of m, n and r. So delta will be equal to n is 0, so 0 square minus 4, m is 1, 4 into 1 into r is minus s upon dab. So that gives us delta as 4s. So minus into minus is plus, so we are going to get it as 4s by dab, which is a positive term that is greater than 0. And since the discriminant is greater than 0, we can conclude that the characteristic equation, it has distinct and real roots. And when that is the case, when the characteristic equation has distinct and real roots, then the method that we are going to use will depend on this thing. We have now concluded that the roots of this characteristic equation, they are distinct and real. Let us move ahead. Let us now check the method. So, since the discriminant is greater than 0, the characteristic equation has distinct and real roots, as I said. Therefore, equation number 3, if that is the case, then equation number 3 will have a solution which is of this form. C dash of s is equal to b1 into e raised to x1 into z plus b2 into e x2 raised to z. In this case, b1 and b2 are constants, and x1 and x2, these are the roots. These are the distinct and real roots of this characteristic equation. So in order to get the solution, we need to find out those roots, and we are going to do that. So in this case, x1 and x2, as I said, are the roots of the characteristic equation. b1 and b2, these are constants, and we will be finding those constants by using the new boundary conditions that we obtained earlier. So the roots, for that I will be using this formula for getting roots of a quadratic equation. So x is minus n plus minus under root of n square minus 4 into m into r by 2m. So this is the formula that will give you roots of a quadratic equation. So in this case, for this characteristic equation, the roots will be obtained by using this equation. X is equal to minus n plus minus under root of n square minus 4 into m into r divided by 2m. Now let us get the roots. So we have the characteristic equation mx square plus nx plus r is equal to 0. Now we are going to get the roots. M in this case is 1, n is 0, and r is minus s upon dab. You know that. Now equation number 3, it has a solution of the following form. We understood it earlier. C dash of s is equal to b1 into e raised to x1z plus b2 into e raised to x2z. b1, b2, these are constants, and x1 and x2, these are the roots which we are going to find now by using the formula. So these are the roots of the characteristic equation. So the roots, they are we are going to get them by using this formula. X is equal to minus n plus minus under root of n square minus 4mr divided by 2m. Now let us use the values of m, n and r. So x will be equal to minus n is 0. N is 0, so it will be minus 0 plus minus under root of n is again 0, so 0 square minus 4 into m is 1 and r is minus s upon db, and in the denominator you have 2 into m, that is 2 into 1 because m is 1. So in the next step it will be x, this is 0, so 0 plus minus under root of 0 0, and 4 into this term is plus, minus into minus, it will become plus. So it is under root of 0 plus 4s by dab by 2. So that is x is equal to plus minus under root of 4s by dab upon 2. Let us continue with this. So that is we got x as plus minus under root of 4s by dab upon 2, and now 4 can come out of this root. So it will be x is equal to plus minus 2 into under root of s by dab and divided by 2. So x will be plus minus, 2 will get cancelled, so it is plus minus under root of s upon dab. So one root, let us denote it as x1, so x1 is under root of s upon dab, and x2 is minus under root of s upon dab. So now we got the distinct real roots for this characteristic equation, and now we are going to use it in this solution to get the final solution. So let us, I hope this is clear to you. If you have any doubts, you please mention them in the comment section. Let us continue with this. So the solution of the equation is c dash of s is equal to b1 e raised to x1 into z plus b2 e raised to x2 into z. We got x1 as under root of s upon dab and x2 as minus under root of s upon dab. So c dash of s is equal to b1 into e raised to, I have used the value of x1, so e raised to under root of s by dab into z plus b2 into e raised to minus x2. I have used the value of x2, so it is minus under root of s upon dab into z. So this is the solution that we get. We have to further simplify it, and for timing I am going to call this as equation number 4. So now next task is to get the constants b1 and b2. These are the constants, and we are going to get those constants by using the new boundary conditions I told you about here. So new boundary conditions we have got earlier. At theta is equal to 0, c dash is 0 for all z's. At z is equal to 0, c dash is cai minus ca naught for theta greater than 0. And the third boundary condition is at z is equal to infinity, c dash is 0 for theta greater than 0. So let us check the boundary condition. So at z is equal to 0, c dash is cai minus ca naught, and this is deviation of cai from ca naught, so I will call it as a deviation variable and I will denote it as cai dash. So therefore at z is equal to 0, if I take Laplace transform of the two, that is Laplace transform of c dash and Laplace transform of c dash of ei, so it will be at z is equal to 0, c dash of s is c dash of ei, yes, c dash of ei of s. So now the boundary condition is written in terms of Laplace transform. Then the other boundary condition is at z is equal to infinity, c dash is 0. That means if I take the Laplace transform, in terms of Laplace transform, it will be at z is equal to infinity, c dash of s is 0. So now we have boundary conditions in terms of Laplace transform, and we are going to use those boundary conditions to get these constants. Let us continue with this. So we have equation number 4, c dash of s is equal to b1 into e raised to under root of s upon dab into z plus b2 into e raised to minus under root of s upon dab into z. Now the boundary conditions written in terms of c dash of s. So at z is equal to 0, c dash of s is c dash ai of s, and at z is equal to infinity, c dash of s is 0. Now we will use the second boundary condition first. So at z is equal to infinity, c dash of s is 0. So 0 is equal to b1 into e raised to under root of s upon dab into infinity plus b2 into e raised to minus under root of s upon dab into infinity. That is 0 is equal to b1 into e raised to infinity plus b2 into e raised to minus infinity, and that is 0 is equal to b1 e raised to infinity is infinity, so it is b1 into infinity plus b2 into e raised to minus infinity, it is 0. So therefore it is 0 is equal to b1 into infinity plus 0, and that is equal to 0 into b1 into infinity, that is b1 will be equal to 0 upon infinity, and 0 upon anything is 0, that means b1 is 0. So in this way we get the value for b1. Now let us get the value for the other constant b2. So first we will use the value of b1 that we obtained in equation number 4. So c dash of s will be equal to b2 into e raised to minus under root of s upon dab into z. Now let us use the first boundary condition. First boundary condition is c dash ei of s. C dash of s is equal to c dash ei of s when z is 0. So c dash ei of s is equal to b2 into e raised to minus under root of s upon dab into 0. That is c dash ei of s is equal to b2 into e raised to 0, and e raised to 0 is 1. So therefore b2 will be equal to c dash ei of s, which is Laplace transform of c dash ei. Laplace transform of c dash ei. And in the next step I will use the definition for the Laplace transform of c dash ei. So that definition is b2 is integration from 0 to infinity c dash ei into e raised to minus es into theta into d theta. You please remember theta here is representing time. So instead of using t, I have used theta to represent time in my discussion. So b2 is equal to integration from 0 to infinity c dash ei into e raised to minus s theta into d theta. So that is the definition of Laplace transform of c dash ei of and the Laplace transform of c dash ei. Let us continue with this. So equation number 4 is c dash of s is equal to b1 e raised to under root of s by dab into z plus b2 into e raised to minus under root of s upon dab into z, and we just got the values for constants b1 and b2. b1 is 0 and b2 is c dash ei of s, and we had used the definition of Laplace transform for c dash ei. So that is b2 is equal to integration from 0 to infinity c dash ei into e raised to minus s theta into d theta, and as I said theta is the time in this case. So therefore b2 is equal to integration from 0 to infinity c dash ei is nothing but deviation of cai from ca naught, and that is cai minus ca naught. So it is cai minus ca naught into e raised to minus s into theta d theta. So that is b2 is equal to cai and ca naught both are constant, so this term will come out of the integral. So it is cai minus ca naught into integration from 0 to infinity e raised to minus s theta d theta. That is b2 is equal to cai minus ca naught, and integration of e raised to minus theta is e raised to minus s theta is e raised to minus s theta divided by coefficient of theta, which is c minus s. So it is e raised to minus s into theta by minus s, and the limits are from 0 to infinity. Now in the next step I will absorb this negative sign, and for that I will have to interchange the limits. So it will be b2 is equal to 1 upon s. After absorbing the negative sign, I will take s out of the bracket. So it will be b2 is equal to 1 upon s into cai minus ca naught into e raised to minus s into theta, and now limits are from infinity to 0. That is b2 is equal to 1 upon s into cai minus ca naught, and when I use the limits it will be e raised to 0, because s into 0 is 0, so e raised to 0 minus e raised to minus infinity. That is b2 is equal to 1 upon s into cai minus ca naught. E raised to 0 is 1, e raised to minus infinity is 0. So that gives us b2 as b2 will be equal to 1 upon s into cai minus ca naught. So now with both the constants evaluated, now we can write equation 4 as c dash of s is equal to 0 into e raised to under root of s upon dab, because b1 is 0. So 0 into e raised to under root of s upon dab into z plus 1 upon s into ci minus ca naught, the value of b2 into e raised to minus under root of s upon dab into z. That is c dash of s is equal to 1 upon s into ci minus ca naught into e raised to minus under root of s upon dab into z, and I am going to call this as equation number 5. Let us continue with this. So we have equation number 5. It is C dash of S is equal to 1 upon S into CAI minus CA naught into e raised to minus under root of S upon DAB into Z. Now in order to get C dash, we will have to take the inverse Laplace of this equation. So inverse Laplace of C dash of S is equal to inverse Laplace of this term 1 upon S into CAI minus CA naught into e raised to minus under root of S upon DAB into Z. So that is L inverse of C dash of S is equal to CI minus CA naught is constant, so it will come out of the integral, come out of the Laplace, inverse Laplace term. So it is CAI minus CA naught, L inverse of 1 upon S into e raised to minus under root of S upon DAB into Z. So inverse Laplace of C dash of S is C dash. So that is equal to CAI minus CA naught into L inverse of 1 upon S into e raised to minus under root of S upon DAB into Z. Now we are going to use this formula. What is that? L inverse of this term 1 upon S into e raised to minus k under root of S. So why this term? Because this term is equivalent to this term. So L inverse of 1 upon S into e raised to minus k upon k into under root of S, where k is any constant. Inverse Laplace of this function is complementary error function of this, the complementary error function of k upon 2 into under root of theta. Complementary error function of k divided by 2 into under root of theta. So we are going to continue with this. We are going to use this formula. So we have this the complementary error function of k upon 2 under root of theta is the complementary error function, as I told you. If you use this formula, it will be C dash is equal to CAI minus CA naught into L inverse of 1 upon S. I have just rearranged it so as to put this term in this form. So it is C dash is equal to CAI minus CA naught L inverse of 1 upon S into e raised to Z upon under root of DAB into under root of S. So in this case, k is Z upon under root of DAB. So we have a term equivalent to this term. So that gives us C dash is equal to CAI minus CA naught is equal to complementary error function of this term k upon, so k in this case is Z upon under root of DAB. K is this thing, so k upon 2 into this term under root of DAB into theta. K in this case is Z upon under root of DAB. So the inverse Laplace of this function will be the complementary error function of Z upon 2 into under root of DAB into theta. You can just understand. So if it is e raised to minus k under root of S, the inverse Laplace is complementary error function of k upon 2 under root of theta. So in this case, k is Z upon under root of DAB. So k, it remains as it is, Z upon under root of DAB, and we have 2 and then theta. So it is under root of theta. So under root of DAB into under root of theta is under root of DAB into theta. So in this way, we get the inverse Laplace of this equation. I hope you have understood the steps. If you have any doubts, you please mention them in the comment section. But in this case, C dash is the deviation variable, which is CA minus CA naught. So CA minus CA naught is equal to CI minus CA naught into complementary error function of Z upon 2 into under root of DAB into theta. That is CA minus CA naught upon CAI minus CA naught. I have brought this term on this side is equal to complementary error function of Z upon 2 under root of DAB into theta, and I am going to call this as equation number 6. Let us continue with this. So we have equation 6, which is Ca minus Ca naught upon Cai minus Ca naught, that is equal to complementary error function of z upon 2 into under root of dab into theta. Now the complementary error function and error function, they are related with each other through this relationship. So if it is complementary error function of capital X, it is equal to 1 minus error function of capital X. So complementary error function of z upon 2 under root of dab into theta, it will be 1 minus error function of z upon 2 into under root of dab into theta according to this relation. So therefore, equation number 6, if it is written in terms of error function, it will become Ca minus Ca naught upon Cai minus Ca naught is equal to 1 minus error function of z upon 2 under root of dab into theta. So therefore, Ca minus Ca naught is equal to Cai minus Ca naught into 1 minus, again I am bringing this term to this side. So Ca minus Ca naught is equal to Cai minus Ca naught into 1 minus error function of z upon 2 into under root of dab into theta. So that is Ca will be equal to, now I am bringing this Ca naught on this side. So Ca will be equal to Ca naught plus Cai minus Ca naught into 1 minus error function of z upon 2 into under root of dab into theta. And what is the significance of this equation? This is an equation for Ca. So the above equation gives variation of Ca with z and theta. So this equation will tell you how Ca changes with z and theta, because you have both z and theta in the equation. So in this way, by taking the inverse Laplace, by differentiating by solving the differential equation with which we started, we have now arrived at an equation for Ca as a function of z and theta. So I hope you have understood the steps. If you have any doubts, you please mention them in the comment section. Let us move ahead. Now let us get the mass transfer rate. We have got equation for Ca. Now let us get the mass transfer rate. So for that, we will start with this relation. Na is equal to Ja plus Ca upon C into Na plus Np. So this is a relation between N type and J type of flux when you have two components. So N type of molar flux of A is equal to J type of molar flux of A plus Ca upon C, where capital C is the total concentration, and Na and Nb, these are N type molar fluxes of E, and Na plus Nb will be the net molar flux. If low mass transfer rates are involved, the bulk term can be neglected. Which bulk term? Na plus Nb, it can be neglected. So in that case, Na will be equal to Je. And if you use Fick's first law of molecular diffusion for Je, Na will be equal to minus dab into dabba Ca by dabba Z, because Fick's first law of molecular diffusion states that Ja is equal to minus dab into dabba Ca by dabba Z. So now our next task would be to get this differential dabba Ca by dabba Z, and we are going to get it from the equation for Ca that we just obtained. So dabba Ca by dabba Z, it is obtained from the equation for Ca. So we have Ca, equation for Ca. If you remember, it is Ca naught plus Cai minus Ca naught into 1 minus error function of Z upon 2 into under root of dab into theta. Now the error function, as per the definition of the error function of x is 2 upon under root of pi into integration from 0 to x e raised to minus x square dx. This is the definition for error function of x. So if you have to write definition for error function of z upon 2 under root of dab into theta, it will be 2 upon under root of pi integration from 0 to z upon 2 under root of dab into theta, as according to this definition. In integration from 0 to z upon 2 under root of dab into theta, e raised to minus z upon 2 under root of dab into theta square of this into d z upon 2 under root of dab into theta. So if you have noticed, we have replaced the capital X with the term. And in that way, we have written the definition for error function of this term, z upon 2 under root of dab into theta. So now we will use this definition. Therefore, this equation will become Ca is equal to Ca naught plus Cai minus Ca naught into 1 minus. Now I have written the definition for error function. 1 minus the definition for error function is 2 upon under root of pi integration from 0 to z upon 2 under root of dab into theta e raised to minus z upon 2 under root of dab into theta square d into d of z upon 2 under root of dab into theta. So that is, now I will differentiate it in order to get dabba Ca by dabba z. So dabba Ca by dabba z is dabba by dabba z of this equation. So dabba by dabba z of Ca naught plus Cai minus Ca naught into 1 minus 2 upon under root of pi integration from 0 to z upon 2 under root of dab into theta e raised to minus z upon 2 into under root of dab into theta square plus d z upon 2 under root of dab into theta. Let us continue with this. So we have dabba Ca by dabba z is equal to dabba by dabba z of Ca naught plus Ci minus Ca naught into 1 minus 2 upon under root of pi integration from 0 to z upon 2 into under root of dab into theta e into e raised integration of this term e raised to minus z upon 2 under root of dab into theta square d z upon 2 under root of dab into theta. So that is dabba Ca by dabba z is, now I have differentiated each term separately. So this is dabba Ca naught by dabba z plus dabba by dabba z of Ci minus Ca naught into 1 minus 2 upon under root of pi integration from 0 to z upon 2 under root of dab into theta of e raised to minus z upon 2 into under root of dab into theta square d z upon 2 under root of dab into theta. Now in the next term, Ca naught is constant, so this will be 0. So dabba Ca by dabba z will be equal to, and Ci minus Ca naught is constant, so it will come out of the differential. So dabba Ca by dabba z is Ci minus Ca naught into dabba by dabba z of 1 minus 2 upon under root of pi into integration from 0 to z upon 2 under root of dab into theta of e raised to minus z upon 2 under root of dab into theta square d z of z upon 2 into under root of dab into theta. That is dabba Ca by dabba z is Ci minus Ca naught. Again I will differentiate the term separately. So dabba by dabba z of 1 minus dabba by dabba z of 2 upon under root of pi into integration from 0 to z upon 2 under root of dab into theta of e raised to minus z upon 2 into under root of dab into theta square in d of z upon 2 under root of dab into theta. Let us continue with this. So we got this equation dabba Ca by dabba z is Ci minus Ca naught into dabba by dabba z of 1 minus dabba by dabba z of 2 divided by under root of pi into integration from 0 to z upon 2 into under root of dab into theta of e raised to minus z upon 2 into under root of dab into theta square d of z upon 2 under root of dab into theta. So in the next term, in differentiation of 1, a constant term, it will be 0. So dabba Ca by dabba z is Ci minus Ca naught into 0 minus 2 upon root to pi is constant, so that has come out of the differential. So it is 0 minus 2 upon under root of pi dabba by dabba z of integration from 0 to z upon 2 into under root of dab into theta. Integration from 0 to z upon 2 under root of dab into theta of e raised to minus z upon 2 into under root of dab into theta square. And in this term, 1 upon 2 into under root of dab into theta, it is constant because we are differentiating with respect to z. So the other terms, they are considered to be constant, so they have come out of the differential dz. So in the next step, it will be dabba Ca by dabba z is equal to it will be minus, so minus Ci minus Ca naught into 2 upon under root of pi into, again the constant will come out, so 2 upon under root of pi into 1 upon 2 into under root of dab into theta into dabba by dabba z of integration from 0 to z upon 2 under root of dab into theta e raised to minus z upon 2 under root of dab into theta square dz. So this is differentiation of an integration. So differentiation and integration will get cancelled and you are left with the term inside the integral. So it will be dabba Ca by dabba z is equal to minus Ci minus Ca naught into 2 upon under root of pi into 1 upon 2 into under root of dab into theta. And now differentiation of an differentiation of an integral is the term in the integral. So it is e raised to minus z upon 2 into under root of dab into theta square. Let us continue with this. So we have dabba Ca by dabba z is equal to minus Cai minus Ca naught into 2 upon under root of pi into 1 upon 2 into under root of dab into theta into e raised to minus z upon 2 into under root of dab into theta and square of that. So in the next step it will be dabba Ca by dabba z is equal to minus Cai minus Ca naught. This 2 will get cancelled. Pi which is under root, it will go into this root. So it will be 1 upon under root of pi into dab into theta into e raised to minus z upon 2 into under root of dab into theta square of this. So that is dabba Ca by dabba z is equal to minus Ci minus Ca naught into 1 upon under root of pi into dab into theta. Now I will square this term. So it will be e raised to minus z square and divided by 4 into dab into theta. So I have squared this term. So once you get dabba Ca by dabba z, now we can use it in the equation for mass transfer rate, which is Na is equal to minus dab into dabba Ca by dabba z. So Na will be Na which will then be function of z and theta will be minus dab, and now I am using equation for dabba Ca by dabba z. So it is minus dab into minus Ci minus Ca naught into 1 upon under root of pi dab into theta into e raised to minus z square upon 4 dab into theta. Let us continue with this. So we got this equation. Na as a function of z and theta is equal to minus dab into minus Ci minus Ca naught into 1 upon under root of pi dab into theta into e raised to minus z square upon 4 dab into theta. So in the next step it will be Na as a function of z and theta, minus into minus it will become plus, so it is equal to dab into Ci minus Ca naught into 1 upon under root of dab. And now I am separating this root, so it is under root of dab into under root of pi into theta into e raised to minus z square upon 4 dab into theta. Now next, this dab can be written as a product of 2 under root of dab. So that is our root of dab into root of dab. So in that case, Na as a function of z and theta, it will be under root of dab into under root of dab into Ci minus Ca naught into 1 upon under root of dab into under root of pi into theta into e raised to minus z square upon 4 dab into theta. Now what will happen in the next step? 1 under root of dab will go with this. So it will be Na as a function of z and theta is equal to under root of dab into Ci minus Ca naught into 1 upon under root of pi into theta e raised to minus z square upon 4 dab into theta. So that is Na as a function of z and theta will be equal to under root of dab. I am bringing this term over here. So it is under root of dab upon under root of pi into theta into Ci minus Ca naught into e raised to minus z square upon 4 dab into theta. Let us continue with this. So we got equation for Na as a function of z and theta is equal to under root of dab upon under root of pi into theta into Ci minus Ca naught into e raised to minus z square upon 4 dab into theta. So this equation, it gives us the mass transfer rate, that is mass transfer flux at any z and theta. So for a given value of z and theta, you can get the mass transfer rate. But we are interested in the mass transfer rate at the interface. that is when z is equal to 0. So for that we need to refer the schematic diagram. So we are interested in knowing the rate at the interface between liquid and gas, and at the interface value of z is 0. So Na as a function of theta at z is equal to 0, it will be under root of dab divided by under root of pi into theta into Cai minus Ca naught into e raised to minus, now z is replaced with 0, so minus 0 square upon 4 dab into theta. So that is Na as a function of theta at z is equal to 0, it is under root of dab divided by under root of pi into theta into Cai minus Ca naught, and this term will be 0, so it is e raised to 0. So that is Na as a function of theta at z is equal to 0 is equal to under root of dab upon pi into theta into Cai minus Ca naught, and I am going to call this as equation number 1. I will call this as equation number 1. So equation 7, sorry. So equation 7 gives us the mass transfer flux as a function of theta at z is equal to 0. It is under root of dab by pi into theta into Cai minus Ca naught. Let us continue with this. So we got equation 7, which is Na as a function of theta at z is equal to 0, that is equal to under root of dab upon pi into theta into Cai minus Ca naught. And now if you write an equation for Na as a function of theta at z is equal to 0 in terms of mass transfer coefficient, it will be Na as a function of theta at z is equal to 0 is equal to Kl into Cai minus Ca naught. And let us call this as equation number 8. Next task is we will compare equation 7 and equation 8. So if you compare equation 7 and equation 8, you are going to get an equation for Kl, the mass transfer coefficient. So Kl is equal to under root of dab upon pi into theta. So this equation gives the point value for the mass transfer coefficient, and the prediction is the point value for mass transfer coefficient is directly proportional to under root of dab. So this equation, it gives the point value of mass transfer coefficient. Let us continue with this. So we have equation number 7. Na as a function of theta at z is equal to 0 is under root of dab into dab upon pi theta into Cai minus Ca naught. Now let us get the average mass transfer flux over the time of exposure, and this can be obtained from this equation by integrating it. So Na average, it will be obtained by taking having a time average value of Na as a function of theta, and this is equal to 1 upon theta into integration from 0 to theta of Na as a function of theta at z is equal to 0 d theta. So that is 1 upon theta integration from 0 to theta of under root of dab upon pi theta into Cai minus Ca naught d theta. That is Na average is equal to 1 upon theta into integration from 0 to theta of under root of dab by pi theta into Cai minus Ca naught d theta. That is Na average is equal to 1 upon theta integration from 0 to theta, and now I have rearranged it, so it will be under root of dab upon pi, and I have separated 1 upon under root of theta. So it is under root of dab upon pi into 1 upon under root of theta into Cai minus Ca naught d theta. Let us continue with this. So we have Na average is equal to 1 upon theta integration from 0 to theta of under root of dab upon pi into 1 upon under root of theta Cai minus Ca naught d theta. And now under root of dab upon pi is constant, so it will be Na average is equal to 1 upon theta under root of dab upon pi into Cai and Ca naught. This term is also constant because Cai and Ca naught, these are constant, into integration from 0 to theta of 1 upon under root of theta into d theta. So that is Na average is equal to 1 upon theta into under root of dab upon pi into Cai minus Ca naught into integration from 0 to theta. 1 upon under root of theta is theta raised to minus 1 by 2 d theta. So that is Na average is equal to 1 upon theta into under root of dab upon pi into Cai minus Ca naught, and integration of theta raised to minus 1 by 2 is theta raised to minus 1 by 2 plus 1 divided by the index minus 1 by 2 plus 1, and limits are 0 to theta. So that is Na average is equal to 1 upon theta into under root of dAB upon pi into Cai minus Ca naught. And this is theta raised to 1 minus 1 by 2 plus 1 is 1 by 2. So theta raised to 1 by 2 divided by 1 by 2. Limits are 0 to theta. So Na average is equal to, I will bring this 2 over here. So it will be 2 upon theta under root of dAB upon pi into Cai minus Ca naught into theta raised to 1 by 2 minus 0. Now I have used the limits. So it is Na average is equal to 2 upon theta into under root of dAB by pi into Ci minus Ca naught into under root of theta. Let us continue with this. So we have this equation. Na average is equal to 2 upon theta into under root of dAB by pi into Ci minus Ca naught into under root of theta. So that is Na average is equal to, now this theta can be written in this way, 2 upon under root of theta into under root of theta into under root of dAB by pi into Ci minus Ca naught into under root of theta. So 1 under root of theta will get cancelled. So this is Na average is equal to 2 upon under root of theta into under root of dAB by pi into Ci minus Ca naught. So that is Na average is equal to 2 into under root of dAB upon pi into theta into Ci minus Ca naught. Now this theta, now I have taken it under the square, under the root. And now I am calling this as equation number 9. So Na average, if you write it in terms of KL average, the average mass transfer coefficient, it will be Na average is equal to KL average into Cai minus Ca naught, the driving force. And this is equation number 10. And finally, you just have to compare equation 9 and equation 10. So comparing equation 9 and 10, you get KL average to be 2 into under root of dAB upon pi into theta. That so means, thus according to this theory, KL, the local value of mass transfer coefficient is under root of dAB upon pi into theta. So as per this equation, KL is directly proportional to d under root of dAB, the mass transfer coefficient. And we got equation for KL average. KL average is 2 into under root of dAB by pi theta. So KL average, it is also directly proportional to dAB. So this theory predicts that the mass transfer coefficient is directly proportional to square root of the diffusion coefficient dAB. But actual observation for turbulent flow is KL is directly proportional to dAB raised to n, where n lies between 0.8 and 0.9. So this theory is predicting the correct thing. It is predicting n to be 0.5, which is lying between 0.8 and 0.9. So as compared to the film theory which we discussed in our previous video, this theory is more accurate. So with this, I will end my discussion for the penetration theory. So at the end of this discussion, what you can summarize in this way. Penetration theory predicts unsteady state mass transfer. It is applicable to mass transfer between two fluids which are in contact with each other and one is under turbulent condition. So since the time for mass transfer is very short, this represent a case of unsteady state mass transfer, which will be defined by this equation. We started with this equation, dou bar Ca by dou bar theta, that is equal to dAB into dou bar square Ca by dou bar Z square. And then we solved this equation subjected to the boundary conditions, and we arrived at equations for the mass transfer fluxes, and then we got equations for the mass transfer coefficients, and we found that according to the penetration theory, the mass transfer coefficient is directly proportional to square root of the diffusion coefficient. So with this, I will end my discussion for this video lecture. I hope you have understood what is penetration theory, what are the prediction of penetration theory. At the end, you just have to remember this dependence of mass transfer coefficient on the diffusion coefficient. It is directly proportional to the square root of the diffusion coefficient. So with this, I will end my discussion for this video lecture. In my next video lecture, I will be discussing the surface renewal theories. So thanks for watching this video. Do subscribe to my channel tell your friends to subscribe to it. Hit the bell icon so that you will be notified as soon as I upload any new video on my YouTube channel. For now, thank you, have a nice day, and hope to see you soon in my next video lecture.